if you didn't understand a certain topic from one book, you can refer it in another book, because there it will be explained in another way. So
Yeah.
you may be able to understand it better from that.
Yeah.
Okay, then we'll start with units now. You should know that there are 7 base units. 7 base units. All the units are derived from these 7 base units. Do you remember them?
Yeah, sir.
Yeah, meter, second, Kelvin, mole. These are the 7 base units. Can you see here?
Yes.
These. Now these are the base quantities. These base quantities have these base units. Can you see the unit symbol? The base quantity. This is the base unit.
Yes.
And also you can see the name is given. Okay, this is the name of the unit. So all the other units are derived from these 7 base units. Yes.
Okay.
You have to remember these base units. Mass, the base unit is kilogram. This is the base quantity, and this is its base unit. Certain students make the mistake of thinking gram is the base unit of mass, but it is not grams, it is kilograms. And another mistake students make is in kilogram, that is this kilo, they write kilo as a capital K, which is not correct. Kilo, we use simple K.
Simple.
Yes. Okay. Time, length, electric current, temperature, and temperature, the SI unit is Kelvin. Now you know there are several temperature scales. We have Fahrenheit, Celsius, and then Kelvin. Okay, the SI unit is Kelvin. And for chemistry, you would have learned mole. Mole is also a base unit. And luminous intensity. Okay, candela. Now easiest is to remember these 3 because you have already seen these, actually these 4 or 5. Okay, candela may be something new to you. Okay, so kilogram, second, meter, ampere. Again, ampere is a base unit. Now you know the equation Q is equal to IT.
Yeah, sir.
Okay, so there coulomb is equal to ampere second. So coulomb is a derived unit. Certain students think when they see that formula I equals Q over T, they think ampere is derived from coulomb and second, but it's not. Coulomb is derived from ampere and second. Okay, so make sure you memorize these base units.
Okay.
Okay, then we have something called the SI unit. SI unit is the standard international unit. Okay, SI, standard international system of units. Okay, system international units. So here S stands for system, I for international. Okay, so international system of units. That's what it means. Okay, because if different countries have different units, they can't work with each other. Because it will be difficult, you have to keep converting. So they have a common unit so that all the countries can work with this unit. What were the subjects that you did for O levels?
Sir, physics, chemistry, maths, and English literature, and yeah, that's all.
How 5 subjects?
No, physics, maths, chemistry, biology, English literature, and English.
How many subjects did you do? 7,
sir.
Okay.
Computer science. Sorry, sir. Computer science.
What were your results?
So my results were 3A, 3B, and 1C.
What were the A's for what? Which subjects?
I got for physics, maths, and computing, and B's for biology and English and English literature.
So 4 A's and 3 B's.
3 A's, 3 B's, and 1 C. So C for literature, A is for physics, maths, and chemistry, I think.
Okay.
The rest is B, sir. Can't remember.
Okay, so should be fine, but you know, certain students think that because they got A's for O levels, they think they can easily get A's for A levels without studying much. but you know, when it comes to A levels, you have to study even more.
Yeah.
So I mean, the O level knowledge, you need that knowledge. It will help you in a way, but that doesn't mean that the student doesn't need to put in the effort much, but still the student needs to put in the effort. So even if a student got a C for a certain subject in O level, they can still get A's and A stars for A levels if they work hard. So it's not much of a difference. Now you would have learned the SI units in the O level class.
Yes.
Okay, so all these units here which you see are base units as well as SI units.
SI.
Yeah, they are base units as well as SI units. Okay, so not all the SI units are, not all the base units are SI units. No, sorry, not all the SI units are base units. For example, Newton. Is Newton a SI unit?
Yes.
Yes, but is it a base unit?
No.
No. Okay, Joule. Is Joule an SI unit?
Yes, but
it's not a base unit. Yes. Now, but all the base units are SI units.
So what's the base unit for energy?
There is no, yeah, so Joule is the SI unit. You should be able to convert it to base units. Do you get it? And how you do that is using the formula. Okay, we will see that. Okay, so all the base units here are SI units. All the base units are SI unit, but not all SI units are base units. For example, Joule is an SI unit, but it is not a base unit. Okay. Okay, so that's what they are mentioning here. Can you see base unit, derived unit?
Yes.
Joule is a derived unit. It's also an SI unit. It's also a derived unit and SI unit. Okay, so let's see that base unit. So you can see these words that are in bold letters are important. They expect you to know what those are. So you can see a base unit. It is in bold black letters, which means you should know what it is. Okay. Then this table is also very important. You see here.
Yeah.
Do you in the O-level class also you would have learned?
Yeah, so we learned
some of it, but not in much detail. Like here, you may have learned from Tera. Okay, starting here, Tera, and then all the way down to Nano, Pico.
Yes, Nano.
Yeah, but in the A-level class there is some more. Okay, can you see that? Pico, Femto, Atto, Septo, Yocto.
Yeah.
And also you see after Tera, Pita, Hexa, Zeta, Iota.
Yeah.
Okay, and also there are some more. Deca. Okay, Hecto.
Kilo, mega. Okay.
Yeah, also you can use call this centi also. Sorry, centi, 10 to the power minus 2. Okay, so here centi, deci.
Okay.
Centi is 10 to the power minus 1, minus 2, deci is 10 to the power minus 1, and these are the symbols. Now, can you see all these numbers from here all the way down? Yes. They are numbers which are less than 1 but greater than 0, between 0 and 1.
Okay.
Yeah, so these numbers are between 0 and 1. Okay.
Yeah.
These numbers here are greater than 1.
Yes.
Okay. Now what you see here is all the numbers which are less than 1, between 0 and 1, have simple letters. Can you see that?
Yes.
All these have capital letters except for kilo and hecto and deca also.
Okay.
Do you see that? So remember, kilo is a simple K.
Simple K.
Yes, like for example, kilometer. So K is simple, M is simple.
Simple. Okay,
kilometer. Do you get it? Because this is something a lot of students make mistakes. They write capital K for kilo. So remember, kilo, hecto, deca, those are all simple, having simple letters as their symbols. But mega, giga, tera, pita, hexa, zeta, iota, those are all capital letters. Mega is a million. 10 to the power 6 is a million. Kilo is 1,000. And here you can see giga. Giga is a billion.
Yeah, sir.
Billion. Tera is a trillion. Trillion. 10 to the power 12. So here it's increasing by 10 to the power 3 each time. Can you see from
Yes.
this to this, it's increasing by 3 zeros.
Yes, sir.
1,000. Then when you add 3 more zeros to the end of that number, it becomes a million. You add another 3 or multiply by 10 to the power 3, it becomes billion, trillion, like that.
Okay, sir.
Okay, so this table is also very important. You have to study it. Okay, so 2 things. The first one is this table, and you should know what base unit is, what derived unit is, and then the metric prefixes.
Yeah, sir.
Okay, so these are called metric prefix. Why do we use the word prefix? Pre means something that comes before.
Yes, sir.
You know, prefix for English you would have learned prefixes and suffixes. Okay, so we use so it like for example kilometer, gigajoule, okay, terabyte. You understand these are prefixes because they come before the word. For example, before meter we say kilometer, something like that. Is that clear?
Yes, sir.
So that's why they are called prefixes. Okay, now we will see how to get this. Now this was your question, right?
Yes, sir.
How you can express this in these base units.
Yes,
in order to do that, you have to be familiar with the equations. Okay, now very simple. We can start with the very first one is F equals ma. Okay. Okay, so here also this you should not memorize this, but you should know how to get these units in base units. I mean, in the exam they may have an MCQ question where they ask you what is the base unit of joule, and they give you a list, so you have to pick the correct answer.
Yeah.
Okay, so those are some of the past paper questions. So let's see how to do this. Now the easiest one is actually this one. Okay, I'll use blue. Okay, so how do you express this now? Let's see. We have let's say we want to write Newton, this thing, Newton in its base units.
Yes.
Okay, now can you see, you remember the 7 base unit? Kilogram is a base unit, meter is a base unit, second is a base unit. So what we do is we write a formula. Now F equals ma. Okay. Now you know this equation, if we use that, Newton is the unit of force. Okay, so Newton is equal to what? The unit of mass times the unit of acceleration. What is the unit of mass? Kilogram. Yeah, so kilogram meters per second squared, because this is acceleration. Do you understand that? So this is how you get this thing in base units. So first thing is you have to know which formula to use. Okay.
Yeah.
All right. Now let's try this joule. Okay. So we want to convert joule to its base units. Oh, base unit equivalent. So now what are the equations that you know? The very easiest. The first thing you learned is what? For which has joule was work done. Or even when you first thing you learned when you learned force was this equation probably. Yes.
Yes.
Okay, so similarly when it came to work done is force into distance moved in the direction of the force. This was the first equation that you'd have learned.
Yes.
Had joule. Okay.
Yeah.
So now it's very easy. So the unit of work done is joule, capital J. That should be equal to Newton, the unit of force, times the unit of distance, Newton meter.
Yes.
But this is not in base units, because you have now meter is in base units, but Newton is not in base units. So we will have to use again another formula which we can use to get this in base units. Can you see that? Which is this one?
Yes, sir.
Okay, so I'll use another color. So now, you know, already we know what this is. So for this, we can substitute that in here. Okay, so what we'll do is now from the previous part, we already know how to do it. Okay, so here we will write what is Newton, kilogram meters per second square.
Okay.
Now, but once you write this, can you see here you will have meter, and here also you will have meter. So meter becomes meter squared. So it will become kilogram meter squared S minus 2. S to the minus 2. Do you understand? So this is joule in SI base. So here you have to use two equations, which was this one, and because this was not in the base units, you have to use this equation. You can do it on the side. Okay, don't use the equation in here. If you do that, it is not correct. So you can do it on the side, then you can use that and substitute here, you will get it. Now can you see that is the same thing they have here?
So like those are the only questions that will be given, like for joules, like some other things won't be given, like the equations, I mean.
No, they will be based on the equations which you have learned. Not, I mean, you should be able to do it if you know the equations. But if you don't know, then there will be a problem.
Okay.
So that means they are expecting you to know the equations. Anyway, you are given a formula sheet. Okay,
Yeah.
so if you are getting confused, you can refer the formula sheet. So see which one has which quantities and which unit you can use. Okay, now again, the third one, power. I think you can do this. If you have that Hodder book, it is actually showing all this working. Okay, so anyway, we'll write now.
So I can download it, right?
Hodder one, I'm not sure whether it's there. I couldn't really find it, but here you have the other books. Actually, the Hodder book is this one. This is the Hodder book, so the new Hodder book. But old one was the black book. You would have seen that black cover book. Yeah, now they don't. I don't think they print new copies of it because the syllabus changed. It was also used for IAL. Okay, it's here. Anyway, so this is the new version of it, which is this one. Okay, this is also available in bookshops. That book is a good book. Now here also, I don't think this book is available on this website. Smart Notes. See, it's not there. Okay.
Yeah.
You can also download the past papers from this website. See, IAL. You click here, and then you can see by unit you can download. They also upload the latest past papers. You can see here, because I checked all the other websites for the 2018 May paper. After a few months after it came out, it was not to be found anywhere, but I was able to find it on this website, 2018 May, June. A few months after the exam finished, so it wasn't any other website. Yeah, so they haven't uploaded October, November. Yeah, October, November 2018 is not there. The recent exam.
Yeah.
The last exam. They may upload it here. We'll see. I mean, that also you couldn't really find it anywhere. Okay. And here also you can get questions. All are past paper questions, classified by topic.
Okay.
Can you see that here? See. So I mean, you can download all this. Because if you take the past paper, the problem with the past paper is the past paper has questions kind of from all the topics. Do you get it?
Yes, sir.
You take unit 2, it has several topics. But if you want, if you classified, if you want questions from only a particular topic, then you can do. Can you see here? Question and also mark scheme.
Yeah.
You see that you said you had some problems with fluid density. See, physics basics. Now you see, I mean, You can download this, and then this is the mark scheme of that. Okay. All right. I mean, you can check it later.
Okay.
Then where were we? Okay. So I mean, this book, the answers are also there. Okay. So these are the answers. I can send this to you. All right. So now if you consider something like power, you have to use that equation. Power is equal to energy over time. Yeah, so then you can use that power equals energy over time. Now energy is in joules, and this, this is the base unit of joule. So power, we use capital P for power, equals energy over time. Now don't write equals joule over second, because power is not equal to joule over second. The unit of power is equal to joule over second. Okay, so that's also a common mistake students make. What they do is they write power equals energy over time, and then they write equals joules over seconds. So that means that power is equal to joule. Power is not equal to joule per second. It's a unit of power, which is equal to joules divided by seconds. And again, see, another mistake students make is they write capital S for second, for unit of time. It should be a small s. Then, like what we did before, this thing you can use here. Substitute that, and then you will get the watt in SI base units. Okay, so it will be kilogram meter squared S minus 2, but here the power is 1, S to the power 1. And do you remember the rules of indices?
Yeah, sir.
Yeah, so here when you divide, you subtract. So minus 2 minus 1. So S to the power minus 3. So kilogram, again simple K, meter squared, okay, divided by meter squared S minus 2 divided by S. So it will be S to the power minus 3. Is that clear?
Yes.
You see, that is the unit. So similarly, I mean Coulomb, Q equals IT, so ampere second. Then voltage, you can try different equations and try to get this. Okay. Now volt.
Sir,
yes.
Sir, can you show how voltage came?
Yeah. So what are the equations? So first thing is you should think which equation you're supposed to use.
So V equals IT.
V equals
IT.
not V equals, Q equals IT.
Oh, Q equals.
Okay, but the problem is now Q doesn't have V. What is the equation? V is what? V equals. Do you remember the definition? The definition of volt. 1 volt is 1 joule per coulomb.
Coulomb.
Yeah, joule per coulomb. So V equals. Do you remember this?
Yes, sir.
W over Q. You should know this equation. This is the definition of voltage, EMF.
So W is
moving a coulomb of charge. Do you remember that?
Yes, sir.
Yeah. So then the symbol of voltage and the unit of voltage are both the same. That is capital V. So again, this is capital V. Here, this V is indicating the unit of voltage, which is volts. So that will be what? Joule per coulomb. Okay. And what else do you know? Coulomb.
Yes,
how do we get the base? It's using Q equals IT. Do you remember this?
Yes, I can.
This is what Coulomb is equal to ampere second. Coulomb is equal to ampere second. Okay. So then we can use that. We can use this for that. And also, joule, this is, we can use this. Yeah, here. Is that clear?
Yes.
Yeah, then when you simplify, you should get this. Do you want me to do it, or can you do it?
Yes, I can do it.
Okay, then we'll move on. Okay, so similarly for resistance, now you have to think which equation to use. R equals V over I. Okay, so you can use that and you can try it. All right.
Yes.
Okay. So I mean, the main thing is you should know which equation to use. So if you use R equals V over I, you can do this at home. Okay, I'm not going to do it completely. So you know V what V, the result of this, you put it in here.
Over
Okay. Ohm, yes, and then ampere. So, and then simplify, you should get this. Okay, so the answer is ohm is equal to that. Okay, then, so I mean, you can do all these questions. Okay.
Okay, sir.
Write this in standard form. What is standard form? Scientific notation. Okay, so this will be what? 9.2 into 10 to the power 6, 10 to the power 9 watt. Because you should know what giga is. Giga is a billion, 10 to the power 9. So this will be 9.2 into 10 to the power 9 watt.
Yeah, sir. 10 to the power 9 watt.
Yes, this thing 43 millimeter. Milli is 10 to the power minus 3. But remember, that is not the final answer. You have to write it in standard form, also called scientific notation, which means your decimal point should be after the first non-zero digit.
So minus 4, sir.
4.3 into 10
to the power minus 4.
Yeah, 4.3 into 10 to the power minus 4. Minus, so you can see the answers are here. Okay, minus 2.
Minus 2, sir.
Okay, because here it's milli. 10. This is 10 to the power minus 3.
Close one, sir. Okay.
Yeah, do you understand it?
Yeah, sir.
Okay, so because the decimal point should be after the first non-zero digit. Okay, so minus 2 means 0. Okay, easier way is, I mean, you can write it out and you can
and then do it.
Okay, I'll show you an easy way to do it actually. Now, if you look at this here, okay, so it's what, 43 millimeters. Now, when you write the metric prefix and the unit, you have to write it next to each other without any gap. Okay. The reason is because if you leave a gap, it means meter. If there is no gap between the two letters, that means this is a metric prefix and this is the unit.
Yes, sir.
If there is a gap, that means both are units. Okay, so here you should not leave a gap. Now, this is how we do it. 43. Okay, so I write multiplication sign, meter. Again, between these two also, the sign is multiplication. Do you get it?
Yes, sir.
Okay, so then it will be 43 times milli. From the table of metric prefixes, you can see it's 10 to the power minus 3 times m. Okay.
Yeah.
Now you can see the problem here is the decimal point is here after the 3. But when we write it in scientific notation, the decimal point should be after the 4.
Yeah.
So now just think about this part only for now. Think of only this part. Okay. So this we can write this part only in scientific notation, just the 43. Okay. So 43, when you write it in scientific notation, it will be 4.3 into 10 to the power 1.
10 to the power.
Just this part. Do you get it?
Yeah.
When you multiply this by 10 to the power 1 or 10, it becomes 43. And then the rest is still the same. So it's 10 to the power minus 3 times m. This is an easy way. If you get a harder question, you can do it this way. Okay. Now what do you see? These two, 10 to the power 1, 10 to the power minus 3. So what do you do when you multiply? You add the powers.
Yes.
So it will be what? 4.3 into 10 to the power
minus 2.
Yes. 1 minus 3, which is minus 2 meters. Is that clear?
Yes, sir.
Okay. Yeah, so like that you can do the other question. So you have to be familiar with the table of metric prefixes.
Yes.
Okay, then I'll just save this so I can send it to you. I'll send you all this after the end of the class. Okay, so I saved it. All right. Then, okay, so you do all this for homework. All right. The answers are here. I'll send this also to you. Okay, both the books I'll send it to you with the answers. Okay, then also, you know, this estimation also you should know. I mean, that means you should have an idea of how big or how small something is in terms of the number. Okay, so for example, you know, a billion. How big is a billion? You should know. Okay, so billion is 10 to the power 9. Yes, not only that, you should also understand how big it is. Now, a billion, for example, if you consider a human being who can live for 75 years of age, if you 75 years in seconds is about 2.3 billion seconds. If you convert 75 years to seconds, it will be about 2.3 or 2.5 billion.
Okay, sir.
Seconds. Okay, so that way you can imagine. So half of that 75 divided by 2 is about 33 maybe 33 more than 35, somewhere around there, right? 35 to 270, yeah, so somewhere about 35 years. So if you count at the rate of 1 second to reach a billion, if you count non-stop, okay, at the rate of 1 second, at the rate of a second, it will take you about 35 years to reach a billion, about 33 years to reach a billion. So can you imagine how big that number is? If you count non-stop, so every second, so 1, 2, 3, 4, like that, if you count, it will take you about 33 years to reach 1 billion. Okay, so I mean, see, order of magnitude scale. So you can see here human height is about this much, 1 meter, something like that. Okay, so human height, typical object. But human height, that is quite small, 1 meter. Is it 1 meter? 10 to the power 0 is 1, right? Yeah, so 1 meter. That's the height of a child.
Yeah.
Because human is a little bit more, maybe 2 meters, 1.1 to 2 meters. Okay. Then ant height, biological cell diameter. So this is the size of a cell. What are the subjects that you are taking right now?
So right now, physics, maths, and chemistry.
Okay. So atom, see diameter of the atom. Diameter of an atomic nucleus. Can you see how small?
Yes.
Then diameter of Manchester in the United Kingdom, Manchester. Have you been to UK?
No, sir.
Okay. Then size of moon's orbit around Earth.
Yeah.
Okay. So that is the radius of the moon's orbit, the distance from the center of the Earth to the center of the moon is this much. Or rather, it could even be the size of, no, it's the circumference. Okay, circumference of the moon's path. Yeah, the moon orbits the Earth, so the circumference, that is this. Do you understand the circumference of the circular path that the moon takes? That is this much. Then this, for the Earth, it is this. Size of Earth's orbit around the sun. Okay, then size of the solar system. So you can see how big that is. Okay, 10 to the power 11, 10 to the power 13. Meters. Okay, so this is for you to have an idea, because why they are telling you this is, when you get an answer, after you do a question, if you get an answer, that answer should be sensible. Do you understand? Otherwise, if you don't get a sensible answer, that means you have made a mistake. For example, let's say they ask you to calculate the time taken for an athlete to complete a 100-meter race.
Yeah.
And you get a time of 2 seconds. Is that possible?
Yeah, so that's wrong.
Yeah, it's impossible, right? Can anybody run 100 meters in 2 seconds? Any human? No. Even the Olympic athletes, it will take about 10 seconds. So that way you have to check whether your answer is sensible. If it's not, then there is some mistake. So to do that, you should have an idea of the sizes of these numbers. Okay, so typical ant height, 2 millimeters. So you know, if you take your ruler and you can see how small 2 millimeters is.
Yes, sir.
Typical human height 2 meters. Now you see here they say 1, but it's actually about 2 meters, 1 to 2 meters.
Yeah.
Okay. Okay, these things I think you can go through yourself and understand. Okay. See, for example, see here height of giraffe, very easy. You can do this and you can also check these answers. Okay, see the estimation part. These are the answers. Very easy. Okay, then that is the end of topic 1. Any questions so far?
No, sir. That's okay, sir.
Okay, then topic 2 now is about motion. Now you said you had some problems with the graphs, right?
Yeah, graphs. So the graphs and those resolving and those stuff.
Okay, that's actually very easy. So vectors, cosine, sine and all, right?
Yeah.
Are you doing M1?
Yes, sir. M1.
How much of that have you completed?
So I think we completed the M1, the whole M1.
Okay, because M1 also has resolving vectors.
Yeah.
Yeah, so I mean these two subjects are related. Okay, this physics and M1 is related to each other. So doing the two subjects will this physics will help you with your M1, M1 will help you with your physics.
Yeah.
Okay. Okay, so over here you should know this again. Do you see whatever is in bold black letters is very important. You should know the meaning. That means you have to study the definition. In the exam paper, they can ask you to define displacement, define velocity, define speed. Then you should write the definition or you should write the formula. So if they ask you to define speed, you have to write this formula in words. Because if you write it in symbols, you have to explain or write what each of these letters mean. Okay, so it's better if you write it in words. Okay, so this is the definition. Speed equals distance divided by time. Same way, velocity is equal to displacement divided by time. This equation. Like I said again, you can write it in symbols, but if you write in symbols, you have to write what each symbol is. So where V equals velocity, S equals displacement, like that. Do you do any sports?
Yes, I do football.
Okay, so do you know what is one whole round around this? What is the distance?
It's around what?
Around this track.
Okay.
Do you watch the Olympics?
400 meters?
Yeah, 400 meters. Okay. So if you see, now let's say they start here. So from here to here, it is 100. Okay.
Yeah.
Then from here to here, it is another 100. Do you understand?
Yeah.
Here to here, another 100. Here to here, another 100. So total is 400.
Yeah.
Okay. And by the way, you have to be familiar with the Greek alphabet, because we use a lot of symbols from the Greek alphabet in physics. Okay, so there are 24 letters in the Greek alphabet. You have both capital and simple letters. And we use a lot of Greek letters. Like I said, if when you learn unit 4, 5, unit 5, like when you learn particle physics, you will have a lot of Greek letters. I mean, almost all the Greek letters are used. So it's best if you are familiar with the Greek alphabet.
Okay.
You can download this alphabet is fine. Here you can see. You can download this and you can study that one. Okay. So I can send you this. I'll send you this link. That's better.
Okay.
Okay, so you can download it there, and you can see here there are 24 letters in the Greek alphabet. You have both capital and simple letters. In the ancient Greek alphabet, they didn't have capital and simple. They had only one upper. They didn't have uppercase and lowercase. They had just one of them, like alpha, beta, the lowercase or the uppercase only. Okay, so here you have upper and lower. Now you can see the first letter is alpha, second letter beta, third letter gamma, fourth letter delta, and the last letter is omega. We have capital omega, which we use as the unit of resistance that we call ohm, and we have simple omega. Now in unit 4-5 you will learn this thing. Okay, omega we use for angular frequency or angular speed. We use this. Then mu you have seen this we use for metric prefixes. Okay, mu 10 to the power minus 6. We use this symbol. Lambda.
So we use mu for?
Mu like micrometer.
Okay, sir.
Yeah, so we use mu micro, 10 to the power minus 6. Then lambda we use for wavelength, theta for angles, symbol we use this symbol, angles. Epsilon, do you remember Young modulus is equal to stress over strain?
Yeah, so epsilon.
And then strain, stress over strain. For strain we use this epsilon. Do you remember?
Yeah.
The equation for Young modulus, yes. Then delta, we have capital and simple. This delta is used to indicate a small change. Did you complete C1? Differentiation?
Yeah, sir.
Okay, in a differentiation, do you remember when you learned the first part of differentiation, how to derive that formula? dy over dx, you had this to indicate a small change in that triangle.
Yeah,
you remember that when you in the textbook, I think you have, they draw the triangle and then they indicate a small increase in x and a small increase in y. There they use delta. So this delta, the simple delta is used to indicate a small change. The capital delta is used to indicate a large change. You would have seen both. Also for other gradient, delta y over delta x they use. So that is to indicate a large change. Small delta is used to indicate a small change.
Right.
Yeah, then we have nu. Now you would have seen, this you have seen pi.
Yeah, sir.
Okay, rho we use as the unit of density, rho. And then sigma, you have capital and simple. Now do you remember when you learn maths, statistics, you used this?
Yeah, sir, for me.
Yes. And also, do you remember this in Young modulus stress? For stress we use the simple one.
Yeah, sir.
Okay, so we use this. Then tau for torque, I don't think you learned that. Epsilon, phi. Okay, under photoelectric effect, you will learn this symbol for the work function.
Okay.
Okay, so you are with the last chapter in this book is about quantum physics. Okay, so photoelectric effect you will learn. Then omega I told you. Okay, so psi. These are the letters in the Greek alphabet. So it's good if you know them because you will use them a lot in physics. Okay, and some people pronounce this wrongly. Okay, so this is pi. This is phi. Okay. Yeah, so delta. So when you have everything here like this, it's easy. You won't get confused.
Yeah, sir.
Okay. Then okay, so do you know what a vector quantity and what a scale quantity is?
Sir, can you see the specimen paper of the IAL new syllabus? Like the first question is about vector and scale, and it's confusing, sir.
Let's see. Unit 2?
No, Unit 1.
Unit 1. This one?
Yeah.
I think I have it downloaded anyway. Yeah, what is the question? Which pair of quantities does not contain a vector and a scalar? So you have to see which one. Now, is acceleration scalar quantity or vector quantity?
Acceleration vector.
Yeah, time.
Scalar.
Yeah, so you should know what a vector is. Vectors have both magnitude and direction. Scalar quantities have only a magnitude or a size.
Oh,
Scalar
okay.
quantities don't have a direction. Scalar quantities have only a size. Size, or another word for size is magnitude. Okay.
Okay.
Vectors have both magnitude and direction. Okay.
Yeah.
And there is actually a table with this. So you can even make a table. Now, when you start learning what vector quantities and what scalar quantities are, you can actually make a table with the list of scalar quantities and a list of vector quantities. I don't think, but the Hodder book has a lot more detail. I couldn't find the PDF of that. I have the hard copy. Actually, I think I can even, but here you don't have the book. That's the problem. But here also they aren't really given, but I think we can also check these revision guides. You can download everything from that website. There are some revision guides also. They should be helpful. Okay. Anyway, we'll continue with this question that we were discussing. Okay, so you already know what a scalar quantity and what a vector quantity is, and like I said before, you should have a list. You can make a list of scalars and a list of vector quantities.
Yes.
Okay, so where's the question? Okay, all right. So vector, scalar, force.
Force is scalar.
No, force is a vector quantity, so you can't make mistakes like this. In the O-level class, didn't you learn about scalar quantities and vector quantities?
Yeah, force is a vector.
Yeah, vector, because it has a direction. You apply a force in a certain direction. Now, we also indicate it in diagrams using arrows. Can you see here? This force, and there's an arrow. So that is indicating the direction of the force. The length of the arrow indicates the size of the force. The longer the arrow, the greater the force. Okay, the direction of the arrow indicates the size of the force. Actually, I have explained this on my YouTube channel. I have done a
Hello?
aspect like this. So they say then when I want, I create a video.
So I can't hear you, sir.
Hello?
Hello, sir.
Yeah. YouTube, you know YouTube?
Yeah, sir.
Yeah, I have a YouTube channel where I upload the lessons, past paper questions and all. I discuss them on that channel. So I have uploaded videos on that channel explaining past paper questions. And when a student has a question on a past paper, like for example this question, so what I do is at times I create a video of this and upload it on YouTube, so that even the other students can benefit. It's free of charge. You can see the videos, and also you can. So what I said was I have uploaded a question on vectors on the YouTube channel. So you can subscribe to the YouTube channel and you can watch those videos. Yeah. Okay. Then back to the question. So force is a vector. Displacement?
Displacement is also a vector.
Yes. So what is the answer then?
So it's B, sir.
Yeah, B. Okay. So here is the mark scheme. You can also read the mark scheme, okay, so that you have an idea of how the marks are awarded, and this way you will have an idea of how to answer the question paper, because you know how the marks are awarded, so you can write your answer accordingly.
Yeah.
Okay, so you see 1B. Okay, anyway, we'll look at the other answers also. Mass, scalar or vector?
So mass, scalar.
Scalar. Weight is a vector, okay? Weight is a vector, mass is a scalar. Acceleration?
Vector.
Yes. So here, scalar, vector. Then this one, velocity?
It's a vector.
Time?
Scalar.
Yes. Okay, so scalar vector. So this has both vectors. So the answer is B. Okay, any other questions like that?
No, that's it.
Okay, and here also you can see which of the following is a derived SI quantity.
Force.
Now see, read the question carefully. Okay, what are they saying? Does it say SI unit or SI quantity? What does it say?
In the sense.
Yeah, so I mean, do you see this word here? It says quantity. It doesn't say unit. We were talking about SI base units. We were talking about SI units and base units. Now here it is not about a unit. It's about a quantity. Do you see that? If you read the question.
So it should be a force, right, sir?
Yes, the answer is what? A. Okay. If you didn't read the question carefully, you might circle D. You might cross D.
Yeah, sir.
Because this is not.
Yes, sir.
Yeah, this is not a quantity. It is a unit.
What? Yeah.
Do you understand? Now, if they said derived SI unit, then it is this one.
Sir, but how force is derived, sir?
Because this is a quantity. Do you remember the 7 base quantities? Force was not in the base quantity list.
Okay, sir. Yeah.
Do you get it?
Yeah.
Okay. So all the others except those 6 quantities or 7 quantities, all the others are derived. Same thing with their units. So the quantities and their units, except those 6, all the others are derived.
Yeah.
Okay. So do you understand my point here?
Yeah.
If the student didn't read the question carefully, they would not see this word quantity. They might think it is unit and then they might choose this one. Do you understand?
Yeah.
Okay, so third one answer is A. Force, yes. Okay. Okay, here this is a good paper. Okay, so you said you had some problems about graphs, right?
Yeah.
Okay, so yeah, this is good. We can go through this. Okay, first before that I'll teach you the other part. Okay, so now I think this is okay. So actually you can okay, so here can you see they say force is a vector, mass is a scalar. They give you a few examples here. We can also wait, I think I have downloaded yeah, can you see this is a this is a revision guide which I downloaded from that website, Smart Notes.
Okay, sir.
See this, you might get a table here. Okay, so you see units and measurements, page 18.
Yeah.
Stephen Popper, the author of this, was the author of that Cambridge O-level textbook. Miles Hudson, I have been personally contacting him. That author, Miles Hudson, he knows me. The author of your textbook.
Yeah.
Yeah, he's in the United Kingdom. Okay, so again you can see this revision guide is also good. Now do you see here physical quantity, this thing we already discussed. Then okay, you have the metric prefixes here, some of them, and okay, this is also there. Can you see they're also giving you the equation which is used to get this?
Yeah.
Okay, so here it shows how to get it also in a way by substituting like this. So quantity, yeah, I mean you can download this also. Okay, about radian also they're explaining. Okay, I don't think it's here. But the harder book there was a good one. Yeah, in your school library, do they have these other textbooks?
I don't think so, sir. They have it.
Okay. I mean, usually if you search online, you can even get this somehow, because I did searched these books online. That's how I came across this website. I found it myself.
Okay. Try to search.
What?
Try to search for that order book, sir.
Yeah. The more books you have, the better, because that way you can also self-study. Like I said, one topic, if you can't understand, you can refer more than one book. Same topic, you can have better understanding. Okay, then okay, so going back to this. Okay, so about average and instantaneous speed. Average speed, you should know the formula. Average speed is equal to total distance divided by total time. Okay, you can even write down that formula. Average speed is very important. Okay, average speed is equal to total distance divided by total time. Did you learn it in the O-level class?
Yeah.
Okay, because just this is now average speed. It doesn't depend on the acceleration or whether the object stopped for some time. It doesn't really matter. Okay, so average speed is equal to total distance total distance divided by total time. Okay, so here it doesn't matter whether there was a constant acceleration or whether the person stopped for a certain time or whether the speed changed. It doesn't really matter. All we need is the total distance and the total time. Okay, so this equation is very important. Okay, average, yeah. Okay, it doesn't depend on the path. It doesn't depend. Actually, it depends on only the total distance and the total time. Okay, by the way, instantaneous speed. What do we mean by the word instantaneous?
The maximum speed.
No, what is the meaning of the word instantaneous? I asked you.
I don't know, sir.
Okay, so instantaneous, instant. What do you mean by the word instant?
Like quick or something.
Yeah, at that particular moment, at that instant, at that moment. Okay. So instantaneous speed means the speed at that moment. Okay, now let's say you are in a car, you see the speedometer. The reading on that speedometer that you see at that moment is the instantaneous speed of the vehicle. Do you get it?
Yeah. Okay.
So anytime you see the reading on your speedometer, that is the instantaneous speed of the vehicle. Because that is actually the speed at that moment that you see on the meter, on the speedometer. Is that clear?
Okay. Yeah.
Okay. So the difference you should know. Okay. So average speed is total distance over time. Instantaneous speed is the speed at that particular instant, which is what you see on the speedometer.
So is there equation or something to measure?
No. Because it's that at that instant. Okay. So there is no equation, but if they give you a graph, you have, let's say they have a graph and they ask you to find the speed at 3 seconds. So what do you do? From the graph you see what is the time 3 seconds, and then from that you maybe it's a velocity time graph. So at time 3 seconds, see what the velocity is, and they may ask you what is this speed. So that is the instantaneous speed. Is that clear?
Yeah.
Okay, so you can do all these questions here. Okay, for homework, finish all the questions, and here the answers are there. Check all your answers. If there is anything, just let me know. You should be able to do it. Okay. No problem. Okay, now here you can see the definitions are given. So in papers, if they ask you to write or define speed, define velocity, define displacement, this is what you need to write. Okay. So you asked me for an equation, right? But there is no equation. The definition is there. See. Okay, so you should. This is very important. Okay, you have to memorize. I mean, yeah, better to memorize, because when it's a definition, why I say memorize is certain students, they write it in their own words, but they miss certain keywords. If you miss certain keywords when it's a definition that you need to write, you will not get the marks. You will not get full marks even. You may get some marks, but sometimes you might not get any marks because they look for certain keywords. Do you get it?
Yeah.
When it's a definition, you can memorize it, but memorize with understanding, because if you write it in your own words, say for example something like this. Now if you say average speed, if they ask you what is average speed, then you are trying to write it in your own words. You write it is distance divided by total time. Is that clear? Is that correct? No, because you didn't write the word total distance. Do you get it?
Yeah.
Okay, so that's why it's best to memorize these definitions with understanding. Okay, so this is very important. This entire box here is important. Okay, because these are all definitions. So in any page, if it's a definition, you have to know it. Okay.
Yeah.
Okay, now can you see instantaneous speed is the speed at any particular instant in time on a journey, which can be found from the gradient of the tangent to a distant time graph. Now, do you understand? If it was a curve, if the graph was a curve, the way you find the instantaneous speed, if it was a distance time graph, okay, not a velocity, it's a distance time graph. Can you see that?
Yeah.
Okay, for mathematics, you learned the gradient. Now, if you want to find the gradient of a curve at a particular point, what do? You draw the tangent to the curve at that point, or you differentiate and get the answer.
In a speed time graph, we can find it, right?
In a speed time graph, you don't find the gradient because that will give you the acceleration.
No, I mean the instantaneous speed.
Yeah, there like what I mentioned before. You see at this time what is the speed? Yes.
Okay.
But there you don't find the gradient. If it's a distance time graph, you want to find the instantaneous speed, find the gradient at that particular time. Because if you want to find the acceleration at a certain time, then from a velocity time graph you find the gradient. Is that clear?
Yeah, sir.
So you should know that the gradient of a velocity time graph is the acceleration.
Yeah.
Gradient of a speed time graph is also acceleration.
Yeah.
Gradient of a distance time graph is the speed. Gradient of a displacement time graph is the velocity.
Velocity.
Do you remember those?
Yeah, sir.
And what is the area under a speed time graph?
Area under speed time graph is a distance.
Yeah. The area under a velocity time graph?
Displacement.
Correct. Okay, so you should know those. So there are, so let's see. Okay, so the first thing is gradient of a distance time graph is the speed. First one. Okay, second one, gradient of a displacement time graph is velocity. Okay, then we have gradient of a velocity time graph is acceleration. Third one, gradient of a speed time graph is also acceleration. That is the fourth point. Then fifth one, area under a velocity time graph is the displacement. And the sixth is area under a speed time graph is the distance. You should know those 6 points. Is that clear? Did you know that? Well,
Yeah.
okay. So because they test you again and again and again. Okay. And I think this, even that past paper question was based on that. Okay. Also, what I suggest is you also download this book. Okay. This Cambridge book. That is also a good book. I downloaded it from Smart Notes. I can send it, but I'm not sure whether it's yeah, this one. This too big to, I think it is too big to send it to. You can download this book also. Okay, this is a very good book.
Okay, sir.
Have you seen this? The Cambridge students use this for their ALS and ALS.
Yes, sir. I have one of the friends. I can ask it even if it.
Yeah, so this is a very good book because it has a lot of detail. Okay, so for example, see this first chapter itself. They have what we were discussing. You can download it for free. Okay. Some pages are maybe missing, like you see here, some pages are missing, but still it's quite good. It's very good. Okay. So you can see here, this is what you should know. Okay, S stands for what? Displacement.
Yeah.
Do you remember the symbols SX? Those are the symbols that we use for displacement. So here we have a displacement time graph.
Then sir, how to represent speed time graph?
Speed time graph?
Yeah.
That is here. Because that book doesn't have much detail like this. That's why I wanted to use this one. Sure, here. Some pages are missing.
No, sir, I'm asking like the symbol is.
Oh, the symbol for velocity is V. Speed also we use V.
Okay. V for speed and both.
Yeah.
Okay.
Yeah, this actually there is a table with all those units. I'll show you. Quantities rather. Yeah, you can actually go through this book, you will see. And here the base quantities and units what we discussed, that is also here. Looks like the page is missing. Okay, here this is the velocity. Yeah, this is what I wanted to tell you. But what was you asked some other question?
Sir?
What was that question you asked about
No,
symbols, right? Okay, symbols. I think it is. Maybe the page is missing. Okay, anyway, okay, so what I wanted to tell you was about the graph. Now, a lot of students common mistake. Okay, do you know any? By the way, do you know what the difference between distance and displacement is?
Yeah, sir. Yeah.
Okay, so for example, let's say a person starts at A and goes to B and then goes to C. He takes this path. Okay.
Yeah, sir.
So what is the distance traveled?
7 plus 8.
Yeah, 15 kilometers. 15. Correct. Okay. What is the displacement?
Sir?
What is the displacement?
It's 10 kilometers.
Yeah. Okay, so the displacement is the shortest distance between the starting point and the ending point. Or we can also say it is the length of the line, the straight line joining the starting point and the ending point. Now, displacement is a vector quantity. So in addition to stating its magnitude of 10 kilometers, you have to tell the direction. Now the direction is from, so we if this is the north, we can say the angle, like a bearing.
Yes.
Okay, whatever 45 degrees or maybe 37 degrees east of north, something like that. Okay.
Yeah.
Okay, and then this is very important. Okay, so I wanted to tell you about this. Now you see here. Okay, so what is the gradient of this graph? Is it positive, negative, zero, or decreasing or increasing?
Increasing.
No, it's constant.
Constant.
The gradient is constant. Okay, the displacement is increasing.
So the gradient is, how come it's constant, sir?
How do you find the gradient of a line?
Like take the y and two.
Yeah, so if it's a straight line, the change in y over the change in x. So it will be the same everywhere along this line.
Okay, sir.
Okay, so the gradient is constant. It is same.
So it's increasing if it is a curve, no? Okay.
Yeah, if it is curving up, it will increase. If it's curving down, it is decreasing.
Okay.
Okay, so you would have learned that if you have something like this, let's say you have a line this way. Okay, if it is like that, then what do you say? The gradient is positive.
Positive.
Okay, so here the gradient is positive. If it's like this, the gradient is zero. If it's this way, the gradient is negative. And if it is like this, can you say the gradient is
increase? Changing.
Do you remember? If it's like this, the gradient is decreasing. Okay, by the way, this is increasing, and also it is positive.
Yeah, sir.
Here it is still positive,
but
decreasing. Okay,
so what's the difference? Positive?
Yeah, positive. Can you see throughout? If you draw a tangent to this line, say I draw a tangent here.
Say if you explain it like a car, like what's the difference between positive increasing and positive decreasing, like in a car?
Okay, we'll see that. Okay, first I'll complete this. That's what those diagrams are for. The diagrams in the book, I want to explain that. That's why. Okay, so first I will just show you this. Okay, then if it's something like this. Okay, so I will show it to you. So if it was something like this, then it is negative. The gradient is negative and decreasing. Okay.
Yeah, sir.
So here it's negative and also it is decreasing. Okay. And if it was something like this, something like this, here still the gradient is negative but increasing. Do you get it?
Yeah.
Okay, so this is about gradients. We use the symbol M for gradient. The letter M for gradient. Is that clear?
Yeah, sir.
Okay, so these are the different curves. So if it's this way, it's positive. Now think of it like this. Now you have this, right? If you draw a tangent to the curve, do you know what a tangent is? It is a line just touching the curve.
Yes.
So anywhere along this, if you draw, okay, it should just touch. It should not intersect. Okay, it's just touching the curve. So let's see. Okay, So let's say like that. Okay.
Right.
Now, can you see the tangent? It's this way. Do you see that? So it's positive. But if you take it here, like this. Okay. So can you see this tangent is still positive, but can you see this is the gradient of this line is greater than the gradient of this line. Do you understand that?
Oh yeah. Sir.
Because this line is steeper. The slope is more of this line than this line.
Yeah.
Okay.
Sir.
So what you can see is when you go along the curve, the gradient increases. Okay. And similarly over here, if you draw the tangent, if I draw tangent here like that. Okay. Then I draw this tangent, another tangent here. Sorry, tangent should just touch the. Okay, something like that. Okay. Let's see, just touching the curve at that point. Okay. Now, can you see here the gradient is higher than here?
Yes.
The slope or the steepness of this line is more than this line. So when you go along the curve, the gradient decreases. Can you see that?
Yeah.
Okay, so here it's decreasing positive, but throughout the entire thing here, can you see it's always this way? So it's positive. Here also it's positive, but over here it's sloping this way. Do you see the gradient is always negative here and here? That's why I got the minus sign. Do you get it now?
Yeah.
So you have to keep this in mind. Here it's negative. Here also it is negative and decreasing. Here it's negative. Negative and increasing. The slope increases. Do you see that? If I draw a line here and another tangent here, the slope has increased, but it's negative. Do you understand?
Yes.
Okay, so let's go back to this. Now this is a displacement time graph. Okay, so here the gradient is constant. That means what is the, by the way, what is the gradient of a displacement time graph? What is the gradient of a displacement time graph?
Displacement time.
Yeah.
It's velocity.
Velocity. So that means here the velocity is constant. Do you get it?
Yeah.
Okay, the velocity is constant. Okay, over here, the steepness, the gradient of this is greater than the gradient of this.
Yes.
Is that clear? So that means this has a higher velocity than this. Okay?
Yes. Sir.
Okay, here the gradient is
0.
So the velocity is 0. That means the object is stationary, it's not moving. Stationary, not moving, at rest, all mean the same thing.
Okay, sir.
Okay, then over here what is happening? Now remember, velocity is a vector quantity. Okay, so the gradient is positive from 0 to capital T, and then it becomes negative. Do you understand what happens here? The object is moving in one direction from 0 to T, and then after that it moves in the opposite direction.
So that means it's not slowing down.
No, that is what I told you. That is a common mistake that students make. Now, do you see the gradient is positive here, right?
Yeah, sir.
And here the gradient is negative.
Yeah.
So velocity is positive and then velocity is negative. Do you get it?
Yeah. Sir.
So the velocity is a vector quantity. So in the beginning it was moving in one direction. So it has a positive value. Then negative value means it's moving in the opposite direction.
Okay.
Okay.
So that means how to show slowing down in the same graph.
Yeah. So that's what we are coming to now. Already you learned this. Okay. So here the speed is increasing. The gradient is increasing. That means speed is increasing. So we'll see that. Okay. What about this? What happens to the gradient here?
Decreasing.
decreasing, because when you go along the curve, if you draw tangent here, tangent here, tangent here, the gradient of the tangent is decreasing, which means the velocity is decreasing. Is that clear?
Yeah, sir, decreasing.
So here the velocity is constant. Here also the velocity is constant, but here constant positive, here constant negative. But they may be different in the sizes. Here it's a constant certain size positive. Here it may be a constant, but it is constant, but maybe another size, but negative in the opposite direction. So the object from 0 to capital T, the object was moving in one direction. Then from capital T time onwards, it's moving in the opposite direction to the original direction in which it was moving. Do you get it?
Yeah, sir.
Say for example, an object was moving to the right, then afterwards it moves to the left. So then the direction of velocity changes. Do you understand? From right to left.
Okay.
Okay. So first thing is, when you get a graph, you see what the axes are. Here the axis is displacement. Here the axis is time. So you have to see what the axes are first. Then you have to identify, after identifying the axis, you should know which rule to use. Do you remember how to interpret the graph?
Yeah.
That's why I asked you, what can you interpret from a displacement time graph? The gradient is velocity. That is what you should know. You should remember. Okay, so first thing is look what the axes are, and then think, what can I get from this graph? The gradient, the area under the graph. The only thing here is you don't know anything about the area under the graph. So you know the gradient. The gradient is the velocity. Is that clear?
Yeah.
Okay, so similarly we have velocity time graph. Now, so what you saw here is displacement time graphs. Okay, so the gradient here is constant. The gradient here is 0. Okay, now we will see velocity time graphs.
Sir, in displacement time graph, the area is what's the area?
No, there's nothing about that.
Nothing.
Yeah, it doesn't have a quantity.
Okay.
Okay, so we have velocity time graph now. It was here earlier. Okay, it's here. Okay, so first thing is you have to see what the axes of the graph are. Then what are you supposed to do? So it's a velocity time graph. Now what can you get from a velocity time graph? You think, after you see the axis, what is the gradient, what is the area under? So what is the gradient of a velocity time graph?
Also, velocity time graph.
What is the gradient of a velocity time graph?
The velocity time.
At once you should be able to tell the answer. What is that?
Acceleration.
Acceleration, yes. What is the area under velocity time graph?
The distance of displacement.
Yes. So you should know that at once, okay?
Okay, sir.
Okay, so from this probably you can get the gradient, we can get the acceleration, and you can get the displacement. Okay, so now next thing is you see the shape of the graph. It's a straight line. So that means, and which way is it a straight line? This way. So what can you say from this?
So gradient is constant.
Constant and positive.
Positive.
So what does that mean? The acceleration is constant and
positive.
Positive. Positive acceleration means what?
Positive means like it's increasing.
Increasing speed, not acceleration, increasing speed. Okay, so the acceleration is constant and positive. Can you see the velocity is increasing? Do you see here the value? It's increasing. Okay, so here the acceleration here is higher because the gradient is higher than here. Okay.
Yeah. So that has a higher acceleration.
Yes, this line. Than this. Okay. Then the other one.
Constant.
Acceleration is
0.
0. Velocity is constant. Acceleration 0 means what? Velocity constant. The velocity is neither increasing nor decreasing. It is staying the same. Okay,
Yeah.
so can you see? Accelerate gradient is 0, acceleration is 0, and you can see the velocity in that graph is remaining the same.
Yeah.
Okay, now this from here onwards is where the students make mistakes. Okay, in these two graphs. Okay, what about this? What first thing is what you see what you can get from the graph. The area under this is the displacement and the gradient is the acceleration. Now here what is the gradient? Is it positive, negative, 0, or what is it?
It's a negative gradient.
Yes, so negative gradient. That means the acceleration is
decreasing.
now listen. What is the acceleration? The gradient is negative.
Yeah,
What is the gradient?
Sorry, sir?
What is the gradient representing?
The acceleration.
Yes, so if the gradient is negative, what can you say about the acceleration?
Acceleration is negative.
Acceleration is negative, not decreasing, okay?
Okay.
Do you understand? The gradient is the acceleration.
So
So
the
that means the
velocity
acceleration is negative. Acceleration negative means what?
Velocity decreasing.
Yes, it's a retardation or deceleration. Yes.
Okay.
Do you understand it now?
Yeah.
Okay. All right. So acceleration is negative. It's a constant. Can you see this is a straight line? So that means the gradient is constant.
Okay.
Constant but negative and negative. Do you understand that?
Yes.
So it is actually this third line here, this one. And you see negative and constant. All three, whenever it's a straight line, it's constant. Okay, so here the acceleration is constant and negative. So the acceleration negative means it's a deceleration, or another name is retardation. And in the deceleration, what happens to the speed? The speed decreases. So can you see here the velocity is decreasing at a constant rate.
Yes.
Okay, then here we have now what can you say about this? Okay, so first thing is the gradient gives the acceleration. So what type of gradients? What type of curve is that? Positive. So entire time the gradient is positive, because if you draw tangent here, here, or anywhere, it will look like this. Is that clear? It's sloping upwards. So that means
it's positive.
Yeah, acceleration is positive. But what else can you say?
The velocity is decreasing.
No. You see the velocity is increasing.
Increasing, but the acceleration is decreasing.
Yes, acceleration is decreasing. The gradient is decreasing. If you draw a line here, if you draw tangent here, and if you draw tangent here, can you see the slope here of the tangent is more than the slope here?
Yes.
Do you get it?
Yeah.
Okay. So that means the gradient is decreasing. Gradient is decreasing. That means the acceleration is decreasing.
Yeah, the acceleration is decreasing.
Yes, acceleration decreasing doesn't mean deceleration.
Okay.
Do you get it? If the acceleration is negative, it is a deceleration.
So if it is positive, it still can be a acceleration or deceleration?
Yeah, it is acceleration. If the gradient is positive, it is an acceleration. But the size of the acceleration is decreasing. Do you understand? Now, for example, let's say in the beginning, the acceleration was 50 meters per second squared.
Oh, yeah.
Then it becomes 40 meters per second squared. 20 meters per second squared. So what that means is, in the beginning, the speed was increasing at a rate of 50 meters per second. Every second, the speed was increasing at 50 meters per second in the beginning. But at the end, what happened? It decreased to 20. The acceleration decreased. So that means the speed is still increasing, but at 20 meters per second.
Yeah.
Per second. Okay, every second, the speed increasing at 20 meters per second.
Okay.
Okay, so still it's an acceleration. Still the speed is increasing. Do you see here?
Yeah.
The velocity is still increasing. The velocity is still increasing, but at a lower rate.
Yeah. Than before. Lower rate than before.
Yeah, lower rate, but it is still increasing. For example, do you drive? Do you drive?
No, sir.
Okay, anyway, you may have experience now. In which gear can you accelerate the highest?
The first.
First gear, yes, correct. Okay, so in the first gear, you can accelerate very quickly. And the slowest you can accelerate or the lowest acceleration is in the fifth gear. Yes. So let's say you start a car. If you want to go fast, it has to be in a lower gear. So when you increase the gears, you can go at a higher speed, but the acceleration is getting lesser and lesser. Do you understand that?
Yeah.
Okay. Another example is of skydivers. Okay, so we'll see that. Now, do you any questions on these graphs then?
No,
they are
sir,
explaining it on the side here. Can you see the slope is changing, the acceleration is changing, but what is the change? The acceleration is decreasing. Okay, so this is very important. Now we'll go to that past paper question. Okay, this one. Okay, so this is actually related to projectile motion. Do you remember projectile motion? Projectile always the horizontal velocity is
0. No, 0.
Constant. Horizontal component of velocity is constant.
So that means we are ignoring air resistance.
Yes. No air resistance. Yeah. Okay, so actually this is related to projectile motion, but by the way, now when you throw something up, it doesn't need to be vertically up. You throw it at an angle, like for example here, 45 degrees. What happens now? If you consider if there was no air resistance, the horizontal component of motion will be the same. It will be constant. Okay, but the vertical component, it can increase or decrease. Now, when it is thrown up, what happens? It slows down. And then when it reaches the highest point, the vertical component of velocity is 0. Then what happens? It falls back down. Do you get it?
Yeah.
When the object is going up, it's slowing down, the vertical component of velocity. Then it reaches the highest point. At the highest point, the vertical component of velocity is 0. Then after that, it starts falling back down. When it is falling back down, the vertical component of velocity increases. When it is falling back down, it speeds up. When it is going up, it slows down. Do you get it? Okay. So here they say a projectile is launched at an angle of 45 degrees to the horizontal, ignoring air resistance. Which pair of graphs correctly show how the vertical and horizontal components of velocity vary with time for the projectile until it lands? Okay, so it's launched at 45 degrees to the horizontal means it's thrown up, not thrown down. Okay, 45 degrees to the horizontal, that means launched means it's thrown up. So what should happen? Which is the answer?
So A.
Okay, we'll see. Now, if you look at A, okay, by the way, again, I told you what is the first thing you have to do? You have to look what the axes are. Okay.
Velocity and time.
Yes, and what is the next thing you have to do? I told you two things. First thing is look at what the axes are. The next thing is you have to see what you can get from the gradient or area under the graph, if possible. Okay.
It's acceleration.
Yes, the gradient is the acceleration. Now, when something is thrown up, if the air resistance is 0, does the vertical component or the vertical acceleration? Now, the acceleration is only vertical. Why? Because there is only one force, which is the weight. Okay. So there is only one force acting on this object or projectile which is traveling in a vacuum, and that is the weight. And you remember, according to Newton's second law, the acceleration and the resultant force are in the same direction. So that means the acceleration I'll save this also. Here it is about the radians. Average speed and gradient. Okay. Okay. So yeah, so what happens now when something is thrown up? Okay, so the gradient, right? So now okay, when something is thrown up, okay, so here we have this equation F equals ma, Newton's second law. Okay, Newton's second law states that the resultant force and the acceleration which this resultant force produces are in the same direction. Mass is constant, so the mass of the projectile doesn't change, that is constant. Okay, so this is a vector quantity, so I'll draw the arrow on top. You remember in mechanics you learned this, in mathematics you learned about vectors, so this arrow is to indicate it's a vector. Okay, so the F and the A are in the same direction, and it is this resultant force which produces the acceleration. Okay, so when the object is thrown, the resultant force is its weight. Do you get it?
Result.
Only one force acting. It's going in a vacuum, so only one force means that force is the resultant force. Do you get it? And the resultant force is the weight. So I can also write for the projectile W equals mg.
G. Okay.
A is g. Okay.
Okay.
W. So the weight causes the acceleration, which is also called the acceleration of free fall. G is the acceleration of free fall, and it is 9.81 meters per second square. Okay.
Okay.
All right. Then we have this. Now again the same thing. Okay. So the weight is what? Vertically downwards.
Yeah.
The G then should also be in the same direction, which is vertically downwards, because it is this weight force which is producing the acceleration. Newton's second law. Okay. This is the resultant force producing the acceleration. So this is also in that same direction. Okay.
Yes.
And the weight doesn't change. The weight of the object doesn't change. So that means the acceleration G also doesn't change. Do you get it? So it's a constant. Do you get it?
Yeah.
Okay. So that means it can't be these two graphs, because here the gradient is changing. Do you understand? The gradient is positive, 0, and it becomes negative. The gradient is the acceleration. The acceleration is 9.81, right? So it can't change.
So A and B graphs would be like okay for like a car going and turning back or something like that.
Yes, that's correct. Okay. No, but no, this is velocity time. Still you can't.
Right.
Because what you said was what? It's going and turning back, you said, right?
Yeah, sir.
If it turns back, what happens to the direction of velocity? The direction changes. Do you get it?
Yeah, sir.
One time it is positive, another time it is negative.
Yeah,
do you get it?
Yeah.
So here the velocity is always positive. There is no change in direction for the first two graphs. So that's why it can't be any of these two.
Okay.
The projectile, if you consider the vertical, see, vertical component, this one, vertical component, in the beginning the velocity is up, and then afterwards it is down. Is that clear?
Yeah.
Okay. So, but the gradient is constant, the acceleration is constant, so it has to be either C or D. Do you get it?
Yeah.
Okay, because the gradient is the acceleration. So first thing is you see what the x's are, and then you see what the gradient or what the area under the graph is. Okay, so here we know it's a velocity time graph.
In C and D, the gradient is positive.
The gradient is negative.
Negative. Sorry, sir, negative. So like where is the there is no change in direction, no, sir.
Why not? See, the velocity is positive from here to here. It's above the x-axis. The y values are positive from here to here. But after that, what happens? The y values become negative.
Okay.
So the velocity from the 0 to this whatever time here is positive, and after that the velocity becomes negative.
So I mean, velocity, the acceleration is negative.
No, yeah, acceleration is negative because they have taken up as positive. Acceleration is down. You can choose whichever direction you want as positive or negative. So if the acceleration, if you take up as positive, whatever is down is negative. Do you get it?
Okay.
Since they have taken up as positive, the projectile is thrown up. In the beginning, the projectile is thrown up. So it is going up in the beginning. So can you see that's why the velocity is positive in the beginning.
So then why is the gradient not positive? Because it's not increasing.
The gradient is, it depends on which direction you choose. Here they have taken up as positive. They have taken up as positive. So it's like this. See. Okay, so we have projectile. Okay, so let's say this is, okay, so this is the ground. And let's say the projectile is thrown from here. And it takes this path. The path is called the trajectory, okay?
Okay.
Trajectory. The path the projectile takes is called a trajectory, and the shape is a parabola. Okay, so now there are two components of velocity. One component is this way. Okay, so let's say this is the initial velocity here. Okay. So I'll indicate it with an arrow. Okay, so this is the initial velocity in this direction. Now the component of this velocity this way, let's call it Vx. Let's say this is V, the actual velocity. And then in the vertical direction, it is, let's say, Vy. Okay, now Vx remains constant. Okay, because it's the horizontal component of the velocity. So throughout the motion, Vx is constant. Now it is upon you to choose, I mean upon them, now they have chosen, it's upon the person to choose which way is positive and which way is negative. If you take up as positive, then whatever is down is negative. Do you get it?
Yeah. Okay.
So what they have done is they have taken up as positive. So I will indicate, so up, positive. Okay, now which way is G? The acceleration of free fall is downwards. Okay, so this is G is downwards. In the beginning, the velocity Vy is up. After this place, after this point, Vy is downwards. Do you get it?
Yeah.
And this G is a constant. And how much is that? 9.81. Okay, meters per second square. It is a constant. So here we can also say G equals a constant. Okay.
Yeah.
And so okay, so we took up as positive. G is always downwards. Do you get it? Because the weight force is always down. The weight and the acceleration due to that weight, which is called the acceleration of free fall, they should be both in the same direction. So here I have what? Weight force. So that is down. That means the acceleration is also down. Do you understand it now?
Yeah, sir. Okay.
Okay. So in this one, now I told you why A and B can't be. So it has to be the C or D. Okay. So why C? Because the velocity, when it is going up, what happens from here to here? The velocity is decreasing. Yeah. So at the highest point, the velocity is 0. Can you understand this?
Yeah, sir.
This point here where this line intersects the x-axis is the highest point.
Yeah.
Because the velocity is 0. The velocity becomes 0 at this highest point. Velocity Vy, okay? Because here this is vertical component. Can you see that?
Yeah, sir.
See the header of this table. Here it is vertical component. Okay?
Yeah.
So at the highest point, the vertical component of velocity is 0. Do you understand it now?
Yeah.
Okay, then after that what happens? The velocity is in the opposite direction now, so that's why it becomes negative. The negative value of velocity is increasing. Can you see that?
Yeah, sir.
Positive value of velocity is decreasing when it is going up. Then the velocity is zero at vertical velocity is zero at the highest point. And after that, the vertical velocity becomes more and more, but more and more negative because the direction changed. Is that clear now?
Yeah, sir.
Okay. Then about the horizontal component, does the horizontal component change?
No, sir. It's constant.
No. So the answer has to be C then. Is that clear?
Yeah, sir.
Fourth one, we'll check the answer. Yeah, fourth one answer is C. You see that?
Yeah, sir.
Okay. Then
So then, so 11.
okay. So then for homework, what you do is you do all those questions, okay? And I also know this part, these definitions are important, okay? I mean, you can go through this book and then motion. Yes, these motion graphs also I discussed. So I was explaining today, okay? So I mean, you can go through these graphs. So can you see here, displacement positive, then after that displacement negative. So that means in the beginning, let's say what this means is something like this. Imagine an object was it started at this point, let's say over here. Okay, the object is here, let's say it starts here, the object is here, it goes this way. Okay, so if you take this side as positive, the displacement or anything that way is positive. Okay, then what happens? It goes and then goes somewhere and then comes back, and then now it goes this way. So if it goes this way from this point, from this level, then the displacement is negative. Do you understand that?
Yeah, sir.
Okay, so here let's say the starting point, and then it goes to the right of the starting point all the way up to 40 seconds.
Yeah, sir.
It's to the right of the starting point. Okay, then afterwards, after 40 seconds, it's to the left. Okay, it goes to the right of the starting point, and now from here it's coming back. Do you get it? It's coming back to the starting point. When it is at the starting point, the displacement is zero.
Okay.
Because the displacement is the shortest distance between the starting point and the ending point. So if it is at the starting point, then the displacement is zero. So over here at 40 minutes, it is at the starting point. Then after that, what happens? It moves to the left. It goes in the other direction.
Okay.
Okay. Yeah, so that is the displacement, and then you have velocity time graph. See, area under, you remember the area of a trapezium?
Yeah, sir.
Formula for area of trapezium. I mean, yeah, you can go through these examples. And then acceleration time graph. Okay, so you can do these questions. Okay.
Okay, sir.
About area and all. So you think you can do this also. And then see, definitions very important. Okay. A displacement time graph is a graph showing the positions visited on a journey with displacement on the y-axis and time on the x-axis. Velocity time graph is a graph showing the velocities on a journey with velocity on the y-axis and time on the x-axis. Okay, then you do all those questions.